I'm motivated to study this because of climate change. And actually, this all started back in 2009 when Dan Arvizu, who was the head of the National Renewable Energy Laboratory, and who also is a New Mexican, came here with a group of people from the National Renewable Energy Lab and said, hey, can you guys help us think out of the box? And after a few hours of talking with them, it became clear that the whole problem of adapting to climate change hinges around technology. Which technologies are going to cost what, when? And so ever since then, I've been working on this, first with a group of people here. A few of you may remember Bela Nagy, who, by the way, disappeared. Nobody knows where he is now. Long, interesting story. But okay, so this is just the ongoing development of that work. Now, it's clear that we need better guidance in the energy transition. I would argue the track record so far is poor. Standard integrated assessment models, which are the main workhorse tool people use for this, compute an optimal transition path based on a given climate emissions target. So that's the question they're asking. And I think it's a peculiar question to ask because it really only makes sense if we had a global dictator who could say, this is what we're supposed to do. And if you believed these arguments about that, we have to make a trade-off between well-being and transition, that might make some sense. But people don't do that, and so models are untestable. You poke at these guys and say, look, your model hasn't been doing very well. They say, oh, well, it's not designed to answer that question. And just to illustrate, here's a picture of projections that have been made. So here is the actual cost with the black dots of photovoltaic solar energy. These red and blue lines are predictions made by various models of that type. The black line there is the trend line from 1980 to 2020. And what you can see is, like, here's a forecast made in 2000 for 2020, and they were off by about a factor of 50, okay? So they were off by a factor of 50, and they were too high on the cost. And they've been making forecasts since even before that, and they've always been too high, way high. And they're high again and again and again and again. And I used to make the joke that the people at the International Energy Agency, somehow they can't plot data on logarithmic scale. Because when you plot the data on logarithmic scale, the trends are apparent. These, by the way, are the projections they made for improvement rates that were reported in 2014, but mostly around 2010, for how much was solar energy going to drop in cost over the next decade. And you can see there was about the order of 3,000 different projections. None of them came close to the actual value, which is that black line. Now, why are these models so off? Well, to do this, I already said they're asking the wrong question, but they also have to make ad hoc assumptions. So these models can get quite complicated. I mean, the Remind model, it picked probably, I would guess, 1,000 person years have gone into building it. And they have to assume things, or they assume things when they make them, like they put in solar photovoltaic, and they use a learning curve. I'll describe what that's about in a minute. And they, but then the model says, oh, do nothing but invest in solar energy. So oh, that can't be right. Prices can't get that low. So they put in floor costs. So these green lines are examples of floor cost in various models of this type. The black line, again, is PV system cost. And you can see it just repeatedly punching right through the floor costs that they assumed were impossible to achieve. Okay. Now, so our modeling philosophy is different. We want to answer a different question. We want to try to predict what will actually happen, and how can we nudge it? And I don't mean nudge in the sense of psychology, but what can we do to incrementally make things better? We want to make testable, falsifiable predictions. One of the problems with these other models, they're completely unvalidated. They just make projections. They don't call them predictions because they don't want to be too assertive. And so we test everything out of sample. We try and understand how good the predictions are, and we want to build reliable models. And we're actually going to do things much more simply. Now, those of you who were at my talk last year or who were at my talk last week will have seen this picture. Doesn't hurt. I thought I'd put it up again because some of you weren't at either of those. And so this is the history of the global energy system over the last 140 years. And on the left, we see the costs. On the right, we see deployment, and we see the different kinds of technologies. So say the dashed black line up there is the cost of coal energy. The brown one is coal energy, the black one is oil, the gray one is gas. You can see that those, they wiggle around a lot, but there's no obvious trend. In contrast, some recent contenders like solar PV, the orange one, hydrogen P2X fuel, meaning hydrogen-based fuels, the green one, wind, that blue one there, they're all coming down in cost in a fairly regular way. In fact, solar photovoltaic energy costs 1/10,000th now of what it did in 1958 when it was first deployed in the Vanguard satellite. And then over on this side, you see the deployment of these energy sources. That green line across the top is traditional biomass. The dashed brown line is coal. The black and gray lines are oil and gas. Then the blue line is hydro. The pink line is nuclear. The dark green line is biopower. Blue is wind electricity. Purple is batteries. And orange is solar PV. And then the green one is, again, P2X fuels. So again, something remarkably different is happening. You see that historically, coal and gas came up exponentially, but at a slow rate compared with what solar and wind and batteries have been doing. It's also notable that nuclear energy initially shot up at a fast rate and then it plateaued out. Okay, so that's just background. And in a sense, what I'm talking about in this talk is projecting these kind of curves. So how do we project the cost curves and how do we project the deployment curves? In fact, I'm not going to just say project. I'm going to say, how do we predict the future of these? And how do we do it in a probabilistic manner so we understand how good our predictions actually are? Jim?
What's useful?
Useful energy. So it's a bit of a tricky thing because you have to make some assumptions. But if you just ask about what's usually called final energy, that's how much energy is there if you could actually get every joule of energy that's in it to do something useful. Useful energy takes into account typical conversions. So if you're running a normal, gas-fired, internal combustion engine, then the efficiency is about 25%. So you take the final energy in the gas and you divide it by 4.
Sort of like a free energy?
It's kind of like free energy, but it's a little rougher than that because it really depends on the way it's being used. But we did that, even though there's some ambiguity in how you do it, because we wanted to have an apples to apples comparison. There's a lot of confusing crap in the literature where people talk about final energy, which is kind of irrelevant. Now, I'm going to somewhat zip through the first part of this talk talking about cost, because I've been working on that for decades, and some of you at least have heard it before. So, but because I don't want to get to the topic of the title I gave, but I still want to say something about it because I think it'll interest those of you who haven't seen it. So first of all, in predicting, it's worth noting that you might think, oh, technological progress, impossible to predict because it's innovation. Innovation's unpredictable by its very nature. Yes, but the rates of progress are highly predictable, as Gordon Moore showed. We'll get back to that. But just to illustrate, here's the cost of various things over a 20-year period in the United States, ranging from hospital services, which, over that 20-year period went up by more than a factor of 2, to televisions, which, at least if you adjust on a quality controlled basis, dropped by 95%. In other words, they went down by a factor of 20 in cost. Huge differences in how these different things behave. Also notice they're very persistent. Televisions didn't just suddenly drop, they drop every year. And we're back to Moore's law, which is quite a remarkable thing. You know, and originally Moore made the statement that the density of transistors was going to double every 18 months. He later on adjusted it to say every 2 years. But since then, that prediction has been remarkably good. Though we've always known it was going to hit a wall around now when things actually reach the quantum scale. So it's unclear what the future of this law is. It seems like it's got to stop. And so this just shows you what I said, that even if the innovations are unpredictable, and actually I remember being in a conference here, David was in the room, Doug was in the room, and it was on innovation and invention and so forth. And there was a guy standing up here who was an actual chip designer. And he said, you know, you guys, you all think Moore's law, it's like God-given, it's just going to happen every year. And I can tell you, every year we'd feel like we were facing a brick wall, and then we'd pound on it, and eventually we'd figure out a way to solve the problems. So well, Moore's law, you know, some people say it's a self-reinforcing prophecy. I don't believe that. First of all, it obviously wasn't before Moore wrote it down. Why did he write it down? Because it was happening before he noted it. And secondly, well, I just think it's caused by other things, though it is certainly extremely useful. And this was driven home to me by Albie Ray Smith, my fellow New Mexican, who is, you know, one of the brains underlying Pixar. And he said at Pixar, they had all the technology ready about 5 years before they could actually make a movie. And they said, look, we just have to wait. We'll polish it up and make it better, but we just need the machines to run faster. And as soon as that happened, they made Toy Story. So they were able to plan, in other words, around that. And in fact, Moore's law did mean that the rest of the industry could plan, assuming that CPUs were going to be faster in a certain date, et cetera, et cetera. It's extraordinarily useful to have a law like this. Now, there's also Wright's law, which is actually much older. It's a little bit different. It says what Wright said, observing, he was in the aviation business, he said that any given airplane factory, every time its cumulative production doubles, the cost of producing the airplane drops by 20%. So works good for airplanes, works good for tons of other technologies. It also works on the global scale as well as on the level of individual factories. So different law, and it's now a power law, which actually means that the rate of progress is slowing down in the sense that you have to have, every exponential increase gives you a 20% drop. Okay, now, so we extended this, we developed a probabilistic method for forecasting technology costs based on historical data. We did a preliminary version of this here at SFI with Bela, and then we extended it to do it better with Francois Lafond and myself and then some other collaborators. And we tested the method by making 6,000 forecasts for 50 different technologies. It worked pretty well, and we applied it to 3 scenarios for the green transition. So again, I'm going to pace through this a little bit fast. You can always stop me and ask questions, but our forecasts look like this. So notice we're not making a point forecast. In a sense, this forecast is kind of trivial. You can see here's past data for solar PV starting in 1980. You can see it's wiggly, but we draw a line through it. We actually just go from the first point to the last point. And from that last line, our model says, well, these are the probabilities of the different outcomes, where there's a 5% probability of being out in the white zone, and each of those bands correspond to a 5% probability. So it's a probabilistic method, and we actually tested the probabilistic method, right? So yeah, in other words, we believe we have a pretty good idea of how good the forecasts are. And to illustrate, we actually wrote the paper where that last circle is in 2013, or that was at least the most recent data. And you can see the subsequent data points, and they're, you know, well within the band that we predicted they should be within. You know, we have here, we then used this method to look at actually 14 different technologies. Some of the ones like fossil fuels, we just used something simpler because they don't follow this rule. The technologies that do follow these kind of laws are somewhat special. But anyway, we built some scenarios to ask about what's the cost of the climate transition be, and is there a way to get there that's cheap? So we looked at the key techs of solar PV, wind, batteries, P2X fuels. We extrapolated the deployment trends. We assumed we phased out fossil fuels over the next 25 years. That's an assumption. I'll come back to it in a minute. And we used P2X fuels for energy storage. So we stored enough. We assumed the world by the end of this 25-year period was going to have enough stored hydrogen that if the sun completely stopped shining, so it was just night all the time, no wind blowing, we could run the planet for a month on the stored energy. Not clear exactly how much you need. Maybe you need even more than that because of intermittency, but it's still a pretty fair amount. We also dealt with all the hard to decarbonize sectors like heat, shipping, air transport, and so on. And we did all those with P2X fuels. In other words, you use solar energy or wind to make electricity, to make hydrogen, to make fuels, and then you burn those fuels for those applications. And we tried to make very conservative cost estimates because we didn't want anybody to accuse us of, boosting our favorite techs. So here are the 3 different transitions that we looked at. Your labels are gone, but there's the fast transition here, the slow transition in the middle, and no transition on the right, or very slow transition. You can see we enormously ramp up electricity, which is shown down here. And that orange band is the role solar plays, the blue band is the role wind plays, the green band is the role hydrogen P2X fuels play, and all the other stuff is, you can see the fossil fuels getting phased out in that plot in the upper left corner. So basically, we assume in about 20 to 25 years, these take over. Now, is that plausible? In our paper, we showed these 3 plots. You see solar, wind, batteries, and P2X electrolyzers. We drew a red trend line. It's plotted on semi-log scale. You can see solar so far, and actually, if you just extrapolated it exponentially, it'd take over quite a bit faster than we assumed. We assumed in that upper blue line that it starts to taper off right now, and then it tapers off even slower, even faster in the slow transition or the no transition. Okay. And this is showing the top panel, the white space is non-fossil fuel. And so you can see by 2040, non-fossil fuels are largely taking over. The blue one is the fast transition. So in the fast transition, most energy is not being provided by fossil fuels by 2040. These predictions are all probabilistic. So here you see the fast transition, slow transition, no transition. So there's still quite a bit of overlap in there. I think we've been cautious in making sure our error bands were big enough that we're going to stay within them. And this shows you the relative costs over here. So if you say take a 2.5% discount rate, then we save the order of 10 to 12 trillion dollars. So we save a lot of money, in other words, by doing this. Why? Because since we go down these learning curves, since renewables, let's just go back to that earlier plot. If these trends continue, you see solar, in particular, wind at a slower rate. By 2040 or 50, they're much cheaper. They make energy much cheaper than it's ever been. And because of that big savings, we end up actually saving money by making a rapid transition. Now, I want to point out that, and wait, let me show one other thing. The plot over on the right here shows greenhouse gas emissions due to energy generation, and you can see by 2060, they're at 0. They're actually pretty close by 2040. Now, I just want to beat my chest a little bit. In 2010, I published a forecast in Nature that the cost of solar PV would be cheaper than coal-fired electricity. And I quote The Economist from 2014, 4 years later, Solar power is by far the most expensive. They thought solar energy enthusiasts were nuts, and yet my prediction was right. Although people, it really irritates me again and again, they say, nobody could have predicted this. And I go, all you had to do is look at the data. I didn't have to be a genius to make this prediction. I just had to look at the data and believe the data, which nobody else seems to have done, or a few others did, but not the main people in the IPCC and so forth. And by the way, this just shows the track record of the simple method we're using. These bands in each plot are the 90% quantiles. So you can see, and making forecasts at different points in time for solar, wind, batteries, P2X electrolyzers, you can see the forecasts for P2X electrolyzers are still kind of shaky based on that data alone. That's because the technology has not been deployed that much yet. On the other hand, that technology is a lot like a lot of other technologies that we have lots of data on. And so it's the behavior we're predicting is in line with that. Namely, it should improve at a fairly decent rate. So you can see these forecasts all did pretty good for all 4 technologies. And okay, I'm going to skip this slide. Now, I'm doing pretty good with time. So what about diffusion? Everything I was talking about until now was about cost. And it was under the assumption that the diffusion, that is the deployment of these technologies, happens at a certain rate, and then we got cost predictions depending on the rate at which that happens. But to deal with climate change, we really have to do this pretty fast. So you might immediately ask, which of those 3 scenarios that I showed you is most realistic? So, you know, I suddenly realized a couple of years ago that nobody has done this problem right. So question is, can we predict how quickly these will diffuse? Thus, how quickly will the transition happen? Well, let's just look at the historical data a little more closely. So here we see solar PV and wind. We see the deployment since roughly 1976 for solar, 1984 or so for wind, and semi-log scale, we draw a line from first point to the last point for reference, or linear regression. And you can see that, well, it's kind of wiggly, but roughly speaking, these have both increased exponentially for the last 45 years. And at a pretty hefty rate, the order of 35% for solar and a little less than that for wind. And if you stare at the curves, there's maybe some hint that they're starting to plateau out, but it's not clear. And notice, solar is, in that period of time, it's increased in its deployment level by a factor of 1 million, 6 orders of magnitude. So huge. And by the way, since we're on this slide, this is an important thing to keep in mind. People go, oh, well, you know, there's still not that much solar and wind. It's only a few percent of global energy generation. But exponentials with high rates of growth are tricky. It's easy to let them fool you because they're small and they're small and they're small, and then suddenly they're really big. So these are about to appear on the stage in a major way. But you go, well, how do we know they're not just going to flatten out? It's totally possible. Okay, well, so to do that, we start getting into technological diffusion. If you look in the literature, there's a long literature saying the deployment follows S-curves. And so, in other words, there's some kind of S-shaped curve, for example, the logistic function that I plot down below, where in this function you have that the deployment at some point in time is equal to the asymptotic deployment level times 1 plus exponential of minus k, which is a rate constant, times t minus t0. T0 is a location parameter that centers where the S-curve is. And so you can take data and fit these kind of curves to the data. And there's a whole kind of story, incubation, rapid growth, maturity, blah, blah, blah. Now, people have tried to use S-curves to forecast what solar and wind are going to do. And here I give you some examples. Let's maybe start on the top left panel. So there's 4 different studies that are colored in. The dots are the actual deployment levels for electricity generation by solar energy. Those gray lines are fits that were made at different end dates. So in other words, we go along and pretend the data's, we're stopping in 2015, we make a fit, stop in 2016, we make a fit. So we make fits every year. Just the only thing that changes, we add one more data point every time we do the fit. And you can see they're all over the place. So obviously, this doesn't work very well. But you'll also notice the 4 published studies that I'm going to beat up on a little bit here are all well below that curve. I'll come back to that in a minute. And some of these made big claims. These guys, Kramer and Hay, I spoke at a conference at Oxford in 2014 maybe, and I was saying, look, solar energy is going to get really cheap, et cetera, et cetera. They said, oh, you're completely full of shit. It's just can't diffuse. It can't take over more than 1% of the energy system. Why? Because of blah, 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 blah about, there's been no example that did that. And that got published in Nature. So, all right. Then here's a couple of more studies. Similar kind of story. And there's wind. Wind's a little different, and a few of them actually are on the high side. But, okay. So it's easy to generate foolishness by just using least squares fitting on this data. And here's another example. That was at national level, global level data. This is national level data where things get worse. There we see Austria, where we see 2 fits, one made in 2019, one made in 2012. You can see they're both utterly different. And you can see the data starts to get a lot bumpier. And in fact, if you delve into it, you can ask what happened there. Well, Austria had a generous policy here favoring the deployment of, this one is wind. And then they removed the policy, and then they instituted another policy. And so you can see these curves get bumpy at the national level. Somehow, though, when you average a lot of countries together, it kind of smooths out. And just another example of the garbage that's been published. This is a paper by Chirp et al. And they're claiming that when you look at the historical data, doing a lot of mumbo jumbo, that you can see that it's just utterly impossible that solar and wind are ever going to provide the energy, because they had actually a good idea. The idea was, let's look at the leaders, the early adopters. Let's see how fast did they adopt and what level did they plateau out. And let's assume the others are going to be kind of the same, and then we can extrapolate from those leaders. Not a crazy idea, except the difference between the leaders and the laggers is not big enough to really tell the difference very accurately. The data is super noisy, and you easily get absurd fits. Like they say, oh, they include only the cases where things have reached maturity, and whether or not something's reached maturity changes year by year. It'll first reach maturity, indicating it's achieved more than 50% of its deployment level. And then next year they say, oh, nope, wrong, didn't achieve 50%, and back and forth. All right, and we actually have now written a paper criticizing all this stuff. I hate writing papers like this because, it's not pleasant. The people that you criticize get extremely angry, but we kind of had to do it because back to Moore's law, it's planning for the pace of the transition. If you believe these guys, then we shouldn't be investing too much in solar and wind because they can't do the job, they're not going to get there quick enough, et cetera, et cetera. So it's a sort of high stakes thing, and as I urge them, we should leave our egos behind. Unfortunately, that hasn't happened. But so we go through and just show, unless you're very careful to not do overfitting, data selection bias, and make other ad hoc assumptions, you can get unreliable conclusions. And I just want to make sure that it was clear that back here, notice these predictions have been completely falsified because they predicted the asymptotic level was here, and it's already here. Okay. Now, this is a hard problem, and there's a good reason why nobody's done it right yet. Several good reasons. First of all, the data's terrible. It's hard to come by. A few, fantastic pioneers have gathered some data and we've made heavy use of them, but it's still, the data sets are pretty bad. The time series are also short. You can see this. Let me actually go back and make this point here. You want to forecast these curves based on this data. This data goes not quite, but almost to present. I guess it goes up to 2021. But the thing is, in an S curve, notice there's not a lot of bending. In an S curve, things start to bend away from exponential growth. But because, well, let me just say, this function in the limit where t is small, it's just pure exponential growth because this term is negligible, right? It's only later that this term becomes comparable to this term, and that's when things slow down. But just imagine trying to predict where this is going to deviate. It's pretty hard to do that. Okay. Now, the growth is inherently non-stationary. When we're doing costs, we assume there's some process that's like Moore's law or a generalization of it, or Wright's law or a generalization of it. They're stationary, Moore's law in particular. But growth is inherently non-stationary because, well, there's, childhood, middle age, and maturity. The deviations from exponential growth are small in early stages. I just demonstrated that. And as I'll demonstrate in a minute, the noise is heteroscedastic, meaning the size of the amplitude of the noise changes during the life cycle of the technology. The noise is heavily autocorrelated, meaning if you're above the standard S curve, you probably will stay there for a while. The noise fluctuations, if you get a big one, the next one's probably going to be big too. And the fitting is strongly downwardly biased. That's why we saw most of those forecasts being on the low side. Now, so how do you think about this? I remember I was making a presentation for trying to get funding to think about this stuff. And one of the people, I said, well, he said, well, we know why solar energy got cheaper. And I go, we do? And he said, yeah, it's because of the Chinese. And I go, well, yeah, but it was getting cheaper at the same rate before the Chinese even thought about making solar energy. And you go, But so I find over and over again, people have there's always a story. With solar energy, okay, we used it in satellites, poles, then, a bigger niche because people started putting little widgets on their lawn and blah, blah, blah. The Germans put in feed-in tariffs and then the Chinese stepped in. So that's the theory I would call one damn thing after another. In contrast, the logistic equation, which I suggested should fit these curves, if we were talking about, say, bacterial growth, we could write down exactly what the bacteria are doing, how they reproduce, the rate at which they die. We can solve those equations, which are roughly, you get a differential equation like this. There's a little death term too. And we can come back to the modifications maybe in the questions. And so that's a deterministic process. And once you've observed the bacteria in the Petri dish long enough, you can predict what their future population is going to be fairly well. Now, I do want to emphasize this work is preliminary. So let's begin by making a model based on the logistic function. We took the logistic function and we've done one thing. We've added this term over here, which is the noise term. And the noise process is now an autoregressive of order 1 process, meaning if that makes the noise persistent, and this parameter rho adjusts how persistent the noise is. If rho is 1, it's so persistent, it's like a random walk. And if rho is close to 0, then it just reverts back really fast. And we find, by the way, it's quite persistent. Rho should be like 0.8. And then this noise here is just a Gaussian IID noise. So that's the model we're going to investigate. And then, let me see what the next slide is. And then we can do a trick that physicists love of making a collapse plot. So we gathered data on 47 technologies. When I say we, I mean my graduate student, Ben Wagenvoort, and with some help from Brendan Tanqua and Leonard Baumgartner, and all the people who collected the data that they gathered originally. But we had gathered from a lot of sources. So we have 47 technologies now, and we plot them in non-dimensional coordinates. So let me go back and explain that. So non-dimensional coordinates, you see k, the parameter k has dimensions of 1 over time, as it must because it's multiplied by something that has dimensions of time. Similarly, L has dimensions of number of things, so we plot them in units where L is by definition 1. K is, all time is measured in units of k. So if things are slow, then we compress time. If things are fast, we expand time so that everything's on the same scale, and we locate them all in the same spot. And so when you do that, you get an interesting collapse plot. This is plotted in what's called a Fisher-Pry transform, meaning we take this sigmoidal S-curve and you make a transform that flattens it out. So now in Fisher-Pry coordinates, the growth is linear. And so you can see that over in this part, you see what looks like a plausible straight line. But in this part, you see all the technologies are looking pretty different. So when we first did this, we said, aha, because the literature talks about stage 1, stage 2, and stage 3 of technological growth, roughly, early, middle age, maturity. And so there we have a way of determining where stage 1 is because we can detect roughly where this transition from this really fast behavior at the beginning, often in a sort of pre-fully commercial stage, and then when it gets on remember this is in Fisher-Pry, this is roughly speaking exponential growth, and then flattening out into maturity. So anyway, thought, great, now we can isolate where stage 1 and gives way to stage 2 for all these technologies. But then we realized that there's another hypothesis we can make, which is called a Gompertz growth process. So in a Gompertz growth process, the derivative is some rate constant k times the log of L over x times x. In contrast, remember the logistic one I did before looks like this. Now, so somehow it seems like there's at least some suggestion that technologies this is maybe not quite as good as this Gompertz process. In bacteria, it's pretty easy to understand why this is true. The kx part is just because that's exponential growth. And then the 1 minus x is that as the bacteria fill up the Petri dish, they have less and less food, so they can't grow exponentially anymore. But so this is some hint that the Gompertz process may be better. By the way, these are just to illustrate 4 energy-related technologies. And maybe I should mention in this set, we have all kinds of stuff. Some of them you might even question whether we should call technologies. So we've got canals, railroads, internet, all that kind of stuff, washing machines, cars, nuclear weapons, ammonia synthesis. We even have nuclear missiles and monasteries. So they all seem to follow very similar S-curves. Now, one thing you realize once you make this collapse is, there's some universality. And in fact, back to my question of how much is just one damn thing after another and how much is deterministic growth, well, we kind of see it here. The signal is that black dashed line, the noise is the variation in all those gray curves, and the answer is that the bulk of the variance is explained by the deterministic function. This is true even though, because back to solar and wind, people go, but there's all this, we have to have all these policies in place, and we have to do this, and we have to do that, and it really depends completely on the policy. How can you even make a forecast without that? Well, all these other technologies, you look at railroads, start reading about the history of railroads, there were huge battles over rights of way, very political thing, a lot of corruption, et cetera, et cetera, et cetera. But so it's partly signal and partly noise, but the signal actually is more powerful than the noise. Now, okay, let's put this and make forecasts. And so here's for solar PV. Now first, let's ask the question, what if, let's suppose you have a strong prior about where it's going to land. You, for whatever reason, believe that solar is going to land, let's say, the current The current level of production, which, let's see, this would be 1% of the power sector in 2022. So let's believe that's where it's going to land. Then oh, that's what's happening. All right. Okay. No wonder. Yeah, much better.
Like that.
Okay, suppose you believe that's where it's going to land, then you can ask, what's the probability for different outcomes given, and here we're assuming a logistic function, and well, look up at, so our prediction would be we'll get to 80% of that asymptote in 2037. In other words, 13 years from now, solar energy will be generating 80% of the power in the grid. And those bands there show you 1 and 2 standard deviation variations. So the prediction's not perfect, but you're at a 95% downward prediction would be 2036, and upward there will be 2030, 2040, right? So surprisingly small band. Why? You start plotting these curves against each other, you see they're not that bendable. We actually tried applying functions with more than 3 parameters, and by the way, already with 3 parameters, it's extremely difficult to get a fit. But you know, you don't actually need those. You get just as good a fit with these simple 3 parameters, because once it's in motion, there's a lot of inertia in this deterministic growth laws. Now the plot on the right shows the preliminary forecast for solar PV capacity without assuming a prior. And this is, I emphasize preliminary again, because our forecasts are going to change because we're tweaking up the method, and I could come back and say a lot about all the work we've had to do to deal with all those problems. But there's our preliminary forecast, and we're actually forecasting that it's going to land more over in here. And so you can see the plot for yourselves. Yeah, so that asymptote's around 16 terawatts. Now, I want to leave room for questions. I want to emphasize, I'm not saying policy doesn't matter and this is all just going to happen inexorably. Policy does matter. Just look at the wiggles in these curves. A lot of those wiggles were probably policy driven. So policy matters. On the other hand, the good news is we've got a lot of inertia going. We do need to deal with things like grid expansion, fossil fuel politics. Land use is a big one because I'm leaving out the 25% of emissions that comes from agriculture, mostly cement. But I still think we're going to see energy get cheap, and it's going to happen fast. Okay, it's not just that, okay, it's cheap, low volatility of energy prices. You could see the way those prices bump up and down. It's actually very bad for the economy when energy prices are fluctuating all the time. You can't anticipate what they're going to be. A lot of things you want to do depend on what energy prices are going to be. And so we should have much less volatile energy prices for reasons I can explain if you want. Better energy security for anybody that has sun or wind, which is almost everybody. Low pollution, much lower pollution, lower environmental impact in general, and much more sustainable, and most importantly, no greenhouse gas emissions. So now you might say, oh, but you're just extrapolating time series. That's true, that's all I've done. We're building models that do other things. I think I already showed this slide in my talk last week. We're, by the way, looking at the labor transition. This is showing that we actually have a big, the good news about the transition is that we're going to get a lot more jobs. It's actually a job increasing thing, at least for the next 2 decades. The bad news is it's a job bubble because a lot of renewables depend on construction, and construction, you do the construction and then you're done. And so it's going to continue to grow at 20 or 30% per year until it plateaus out, and energy growth only grows at about 2% per year, though it may start growing a little faster once we get there because it's going to be so cheap. So we're building, just as a, you know, a trailer for future research, an agent-based model of the energy and power sectors. The agents are real energy and power firms. We have a massive data set showing for the last 25 years 90% of the power plants and oil fields and everything in the world, together with who owns them, and data about costs, balance sheets of companies. So we're putting that together to build an agent-based model where the agents are the energy and power firms. Every year they may or may not invest in new assets, like they might drill a new oil field or they might build a solar farm. And then we simulate the market every year because the landscape changes. We simulate the market, we find prices and quantities sold, and we estimate the profits of each of the companies, and we predict the future costs of technologies. We do it year by year. And now we have a policy laboratory because we're going to do this for the whole globe. We just got a $4.6 million NSF grant. Hallelujah. And so we're going to do it for the whole globe for solar, wind, oil, gas, coal, and hydro, so that we can really look at the entire energy system, how the pieces compete with each other, and put in policies and see how the system responds to those policies. Yeah?
Yeah, so I'm a little bit confused. Your message before a little bit was that policy doesn't matter. Look at
No.
these things. We only care about the technologies. We can just do the plus without paying attention to all the corruption around railroads, et cetera, et cetera. But now you're saying that actually the main motivator is to figure out which policy to use.
Yeah. So I didn't say policy doesn't matter. I'm saying that a lot of the action is just in the technology itself, but policy does matter because, as I said, there's a lot of fluctuations around these curves, and you could see actually quite graphically on the Austria one I showed you back here. Look at Austria to see that policy matters. Again, there's a favorable policy here, the policy gets shut off there, policy gets re-implemented here. So policies do matter. It's just that, and all this data included lots of policy stuff in the past, some of it more than others. So it matters, but it isn't everything. That's my point.
Okay, so
Okay.
related question then, and then I'll shut up. You said you are not going to assume that we have a dictator for how the world
Right.
things. Bummer. But then you also said that those policies at the level of Austria, for example, that when you then look at the entire world, all that washes out. So who would be implementing the policies that you are investigating?
Yeah. So every country has their policy. Actually, in the United States, frequently states have policies, even cities can have policies. And so we're going to do this as best we can, given how complicated the policy landscape is. But we want to build this model for several reasons. One is because I want to demonstrate to the fossil fuel companies that they're about to go out of business unless they get on board quickly. I think that will help accelerate the transition. But in general, we want a policy laboratory where we can play with it. So we could say, let's assume Germany has this policy, the US has this policy, China has this policy. What happens? And we can now play around with policy scenarios that may be quite complicated. So hopefully that answers your question. And so anyway, this is the way this model works. Basic elements are the firms and the plants. We have an investment module. Some firms go out of business. We update the costs. We run the energy market and we go around the loop. And we're already doing this for Texas Power Grid. We picked Texas because Texas, ERCOT as it's called, you can see there's a little bit of Oklahoma in there and you're missing part of West Texas, but it's its own power universe. It's an isolated power grid. So we can model it and we've seen that we already have a pretty decent model. We can predict things about the generation mix. We can predict things about energy prices. The predictions aren't perfect yet, but I think it's all quite doable. Now, I think that's the end of my talk. Thank you. Yes?
Clarifying question is, in your proposed model, is the policy endogenous or is it imposed?
In our proposed model, you mean the one I was talking about at the end?
Yeah.
It's imposed. The policies are at this point exogenous. Now, My student, Penny Mealy, my student as of 8 years ago, Penny Mealy, who's now at the World Bank, has been studying policies. And I think there is some hope for somewhat endogenizing policies, because what she did is get a big database of policies and classify the policies according to types and look at the time history of the policies so that you can actually understand which policies are feasible for which places when. And so with that, coupled to this, we may be able to really go even deeper. So any other questions? Andrew?
Do you have some intuition for the Gompertz growth process, where you have now the difference of the logs versus the actual difference between the, so you have in the Gompertz growth, the logs, right?
Yeah, yeah,
The logistic, you just have the difference of the two.
yeah.
Do you have a good like analogy for the intuition behind that? Of what
No.
No.
I would love to have some. You know, it's a good question. And we're thinking about it quite hard, but it's a great question. Sam?
Thanks for a great talk, Don. You mentioned canals and monasteries.
Yeah,
And is it, but you also described the inertia and so on as a technological inertia. Well, clearly the case of canals is not primarily, you're talking probably, is it canals in the US?
actually, globally.
Globally?
Yeah,
That's driven by public policy. And whatever monasteries are driven by, it's not technology. So
Yeah.
Is it just a quirk that they also work?
well,
Or does that suggest there's something else going on that's making the S curve happen that shouldn't be called technology?
yeah, probably the latter. I think there is some universal process back there. And by the way, we might have a hard time distinguishing logistic from Gompertz technology by technology, because the data is pretty noisy. But you know, on one hand, yeah, canals are heavily driven by policy, but on the other hand, there's a period where people went, wow, canals, they started digging a lot of them, at least in the developed countries. And then actually you can see that as canals are, before they fully reach maturity, railroads come in and outcompete canals. A lot of the legislative and, you know, competition was between canals and railroads. So, and of course, monasteries, again, I don't know, now we're talking about cultural diffusion. And I think it's just that when you have growth processes where a limit and where there's a possibility of some kind of replication process, you know, you make one monastery and people go, wow, I want to join a monastery too. And they go off and start another one. So somehow it's infectious in some sense. So I think some of the qualitative elements are probably very similar.
I think it's a confusion.
David?
It's talking about diffusion, not the invention.
Yeah, this is diffusion.
That's diffusion. And I think for invention, your criticism would hold, right?
It wasn't even a criticism.
And not a critic, but the observation.
I was asking about it.
But yes, but diffusion,
Yeah.
who cares? Monasteries, canals, integrated circuits, that's a common mechanism. That's a mechanism of persuasion.
If it's a common mechanism, then Don is wrong to say there's technological inertia here, because you have the same.
Yeah.
Whether it's a monastery or whether it's a chip photovoltaics, then clearly that analogy doesn't hold. And that's not exactly a criticism, but it's.
Yeah. I'm using technology in a very loose way.
Yeah.
I should have made that clear.
Like-
So I would call monasteries are in some sense a social technology. Nuclear missiles are, okay, that's obviously technology, but canals are a technology.
Sentences you said about people catching on and so on.
Yeah,
That's a social technology.
yeah,
There's something similar going on. Yeah.
Yeah.
I can see
yeah, yeah,
call it technology, but whatever it is, I could.
yeah. We need some nice name for these things, whatever they are, that seem to behave the same way.
It's incredible that we found that out.
Melanie?
So you showed like the price of nuclear is pretty flat, I think, with your slide over time.
Yeah.
I'm wondering if that's more a policy issue or a technological issue? And do you think that nuclear has any place in this?
Yeah, yeah. So first of all, it's not a policy issue, because lots of countries have nuclear power. They've had very different policies. The French have been super gung-ho, the Koreans, but in no case The Koreans managed to get nuclear power to come down at a rate of 1% per year. The French have not managed to get it to come down. And in the US, it went up by a factor of 3. So I could attribute the factor of 3 to regulation. But the fact that in almost exactly the same period, solar PV went down by a factor of 10,000 and nuclear was at best flat, tells you there's very different technologies. People are trying to understand why is it one thing's this way and one thing's the other way? Well, nuclear reactors are bespoke things. They're not really manufactured, although the French and the Koreans both tried to standardize them. But they're not very modular, whereas things that come down tend to be things like integrated circuits that you just print, or that you can manufacture in a highly modular way. But the evidence for this is still pretty loose. And so it's hard to predict a priori from just characteristics. Actually, the main theory that gets quoted is one that James McNerney and I developed and Sid, where we built actually on earlier work by Stuart Kaufman and Jose Lobo, where they said, what happens if you just, and actually goes back to John Muth, who was actually, ironically, the inventor of rational expectations. So I also made a dart throw model of technological change. And so he was willing to go either hand. And so Muth made the dart throw model, Jose and Stuart, et cetera, improved it, and we improved it another notch. We improved it so that we could look at actually how does the modularity of the technology affect the rates? And we were able to show that more modular technology should have faster improvement rates. So a couple of people have tested that. With enough hand waving, it's true, but it's not highly predictive because the error bars are pretty big and modularity is hard to measure and so forth. Yes?
Question, is it possible to go back to where you compare the different predictions? You said one prediction goes this way and the other one goes
Yes. So which prediction did you want to look at?
graph. Oh, is it I don't remember which graph, but I'll see.
But describe the graph a little more, because I've got a lot of predictions on this graph.
Yeah, it had a pink and a green,
Pink,
black dots.
pink and black dots. Okay, let's see.
This one's, you know.
Yeah,
this
that
guy's
maybe
going
this one.
this guy-
Yeah, these ones.
I can't see anything.
What? Oh, sorry, we're not projecting anymore. What happened? What?
I think it's auto switches off.
Well, I can,
Oh,
if
okay.
people can remember this.
Is it easy? Could somebody switch it back on?
Well, no, just, there's a button next to you.
What?
There's a little
The remote control.
remote.
Okay.
It is a question about what was discussed before.
Yeah. Say your question out loud and maybe eventually we'll get the camera back.
Yeah.
So, but what's your question?
It's a question of what was discussed before, which is how to combine inertia, first order inertia with the S curve,
Right,
which if I understood. the
right.
conversation.
Well, the S curve
So
already incorporates the inertia, but let me ask the question maybe you meant to ask, which is, there is some combination of these two things. And actually one thing we're trying to do is to understand how do policies affect things? Why is it not showing the right screen?
It's not screen sharing it.
What?
I think it's not screen sharing anymore.
Yeah, okay.
Also probably your second desktop, so you're gonna win.
Okay, well, we may just have to give up on this because, unless somebody can come fix it, because I can't deal with it right now. But we are trying to understand how effective are policies, and so we're collecting a lot of data to try and look, do the cause effect thing. What kind of policies produce what kind of effects? And so there's a serious problem to do, but that has to be combined with the inertial component.
can I ask my question?
Sure.
Yeah.
Yeah.
It was a brilliant question that I would have asked.
Well, I knew you would have.
Thank
All right.
So you made a point, I will just describe what I saw, okay?
Yeah.
You made a point that this curve, here's the real curve, and here's the other curve, and it's
Yeah.
slower. The difference in years was 8 years.
Yeah.
And so if you think of, if you have these technologies and it's kind of first order inertia, but then you try to predict when they turn over,
Mm-hmm.
saturate.
Yeah,
You have to separate out, I think, the inertia, the first order component of that, and ask when during developmental time do I gain enough information
that's,
to predict, to responsibly or accurately?
yes, no, that's, yeah. Let me, oh, wait.
I'm happy if you want to answer.
No, go ahead.
I haven't
Finish
stated
the
my
question.
yet.
All right.
So so that's the L. My point is that the question then becomes a long time when things change. At what time can you predict L correctly?
Right.
Saturation.
No, that's one of the main things we're doing in our paper.
And if you start thinking about that, you realize that L may change. You may have very little information about L, and L may. So that becomes then an issue of competition, of the the costs actually. So it's kind of an assembly process that has to do with the first order diffusion things, but also with policy. So I'm wondering if you even separate out L more or less about the 8 years, and maybe just say how can we kind of predict the future L, whether that's redefined.
Yeah, yeah. So I should have been a little clearer. We are, one of the key innovations we've made to solve this is to actually use proper Bayesian methods, taking into account all those effects I listed, and working very hard to get rid of this huge parameter bias. But the question we're asking is not just let's make a prediction right now, but as a function of where we are, how accurate is that prediction? And those error bands that I showed you are saying right now, we think that's how accurate it is. If I'd gone back and made a prediction 10 years ago, the error bars would have been much wider, because we're getting to the point where we can just begin to detect the deviation from the exponential. 10 years ago, it would have been invisible. So when the paper comes out, we'll be doing exactly what you said. Now, separating out the policy part from the deterministic part, it's tricky, but clearly when you look at the national level, you can see the bumps in the curves caused by the policies, and we want to understand better how to influence those bumps in the curve.
So the opposite reading of your talk is that all of these terrible predictions you showed us didn't matter because investors and scientists got together and acted in a way that in effect falsified them. And yet you seem to be expending a large amount of energy on making better predictions. So why? Why?
Because go back to what I said about Moore's Law and Ellie Ray Smith. It was critical that he could say, in 5 years, investors, I'm asking you for $100 million. Finish this thing. We've got all the technology in place. Moore's Law will deliver it for us in 5 years. That's huge, okay? And in fact, I would, the fact that the predictions have consistently underpredicted deployment of renewables, predicted excessively high costs for the last 20 years has slowed them down. If it hadn't been for that, we'd have more than we have now. So I'm not saying everything is, just preordained and it's going to happen regardless of what we do at all. It really does matter. But the technology and its usefulness and so on dictate a lot about how things are going to go. Dan, nice to see you.
I would say that probably a lot of it depends on actually articulating a mechanism, because otherwise people just have to have their faith.
Yeah.
So that when you can refer back to some whatever segmented production cycle, uptake, all these things, that's the thing that convinces people.
Yeah.
Just don't be smart, but I don't know.
Yeah.
So,
well,
I mean, you know that, but
no, I understand.
I think
And back when we were seeing the logistic winning, we thought, great, I can explain that. I had a nice little story. I wrote a draft. There's 2 paragraphs with a mechanism. But if Gompertz is really better, as it suggests it is, although right now, what we're just doing right now is doing the head-to-head forecasting competition to see which one forecasts more accurately. Gompertz is a little bit tricky because it's a stiffer equation in some sense. And so, but if it's Gompertz, then I'm a little puzzled. If it was logistic, I could tell a story that's kind of like bacteria. For instance, on the consumer side, the more people have it, the more people see that, oh, your friend has it, now I need to get one. But you saturate the market at some rate, 1 minus X. So it's kind of the same story as the bacteria.
I guess one thing I wonder about is how much of the underlying innovation processes, production processes kind of washes out in the noise? Like what's the principle? I mean,
Yeah,
you know much better than I, like generic principles of technology development that have some hope of adoption.
hmm
They gain a foothold. How to, you know, again, depending on what kind of technology it is, how does that feed back into the cycle? You know, in this sense, transistors are kind of easy.
yeah, yeah,
Whatever, the physics of it was pretty well understood. But here, I think, I mean, there are a lot more moving parts, and to the extent that you could abstract different industries,
yeah,
what dovetails back
yeah,
be interesting.
Can I just add on to that as well? Because it depends on so many other things. So it's, as you say, the grid is completely essential for that. And as it talks about, it's complex. But you've made a decision that, in a way, from what I hear, because you're saying, well, the models are wrong and hence people are not investing. So you want to have the right models so that people invest in renewables, which is great, but it's still an opportunity cost. It still means they might not invest in other things.
yeah.
So you're making a decision that that's what's worth investing on.
Oh,
But it means that there are other things that could be invested
by all means,
happen. So is it necessary?
by all means. And let me just tell you the things I don't want to happen is massive investment in small modular nuclear reactors, which you might as well just tear up dollar bills because it ain't going to work. Just isn't going to work. You just look at the history so far of that technology, it's not going to win. It's also because it's so, and I could list a few other things that people are investing billions of dollars in that are wasting money. Now, what?
Shorting them?
I am looking for a way to short them. I am.
Some that are not wasting money. And
Well,
for example, the IEA is now putting a lot more effort, as is the IPCC, on understanding behavior change. And I know you're saying we can't do behavior change. We need to do
Yeah.
technology. But when you do technology, that means you're disinvesting in behavior change, and you're going in a different direction. So you're creating a world that is going to be technology.
Yeah.
And that's now you're making. So you're
Yeah.
in a way your models are making a policy decision.
Yeah. Well, my models aren't making the policy decision. My models are just using, you know, these are just facts. But,
I don't think, and I
but
just quickly, I don't think there's confusion here because there's a way of talking about Moore's law, which was transistor density, and then it was then it was parallelization, then it was system on a chip. It's not one mechanism, right? We know that. And so the technology story is not the right causal explanation. It's human ingenuity. What you want is a model of collective intelligence, not a model of matter. And I would suggest then to your point, Audrey, that I think Stone's results, the story he's telling is technological, but actually it's a story of ideas.
well,
When
yes and no.
monasteries, so I think social change is in his data.
Yeah. No, social change is in the data.
Yeah.
But let me just stress the key point, and this goes back to Audrey's, I mean, it's a very good question. It goes back to that because what you see when you look at technologies is that people can exert a lot of effort as measured, say, by R&D or production. In some technologies, costs don't go down. So that investment doesn't pay off in that way. Other technologies, Moore's law is the best. You know, transistors have increased at a rate of 100% per year since then, dropped in cost by 40% per year, and there are now more transistors than there are synapses in human brains. And so on the whole planet. So, so it's an example where that effort was extraordinarily productive. Nuclear power is an example where the effort has been extraordinarily unproductive. And at some point you have to listen to that story. Now I'm all in favor, we should keep investing in new technologies, and we should also think about what we can do with social change. I don't think the two things are exclusive, and I don't think the budget for technological progress is at least directly eating the one, except if people go, well, technology will solve the problem, we don't have to become cavemen again.
But what happens is that, for example, the work that I do, which is cities, you say, okay, well, we have now renewable energy, so we can all go in electric cars.
Yeah.
What does it mean? We create the same old cities that are made for cars. Are we better off that way? Not necessarily. So the investment, once you've invested in the whole system for electric cars, the same way we've invested in diesel cars, we create a system very hard to extricate ourselves.
Yeah.
Same thing for cars, for electric cars. We then create a system with electrical charging systems. People buy their cars. We create the streets and the networks, and that means we're disinvesting. We're not investing in something that could be much more radical change that would have many more benefits, not just climate change. So it's not. There is, I think, an opportunity cost and a lock-in that happens.
Yeah, but would you rather have that or another degree of warming? Because I think,
That's what I'm saying is that
yeah, but you really think people are going to just change their habits? And,
no, you're not.
yeah.
Not saying you just tell people to change their habits. You
Yeah.
change the cities. You
Yeah,
change
yeah.
the urban environments. You change the land
Well,
uses so that people can.
I'm all in favor of that.
Those aspects of cities are a limiting factor with climate change, right? It's all of the power consumption, building generators, and like that's the bigger part, no, of.
It's all transport is the one area
But-
that keeps growing, right? So transport is
But I guess the question is, what is the choice to you? Yeah, is the choice, either you convince people not to use cars, which I would be in favor of if we could do that, strongly in favor of. I hate cars.
It's making the cities happen.
Well, you have to somehow, yeah, it's true. And you look, say, at Oxford now, Oxford is extremely automobile unfriendly, which is great because then people can bike in the city and lowers pollution levels and so forth. But that's happening along with solar energy getting cheap. I don't think the two things are.
But that's
Yeah.
the thing is I think when you focus on one area and you don't look at how it has implication elsewhere.
Yeah.
Not one to preach on that, far better than I do. But I just think I worry a bit when I see this, and I'm trying to understand the motivation behind it, because I do think that we're putting our attention away from things that can be much more beneficial for climate change and much more.
But we need both, don't we?
Yeah,
We need both.
It's not one or
So
the
you do that one, I'll do this one, and then as a team, we do more than we would do if we were both doing the same thing. So I think it's a division of labor.
Confused.
Yes.
Still, I mean, what's been swirling around is policy versus some inexorability in the technology, and then there's behavior change. But can you explain, maybe I just missed something, the nuclear power flatline versus the drop it comes to, so is that because of some sort of match between the attractiveness of the technology and human psychology? In other words, is there a
No.
mapping that's
No. I don't. I just think it's has to do with, how much does it cost to build a nuclear reactor? How much does it cost to maintain one? I remember reading this story about a leak at a nuclear reactor in Vermont. To deal with this leak, you have to have little robots that go around, and you have to have, it's extremely hard.
ultimately has to impact on a human saying, I don't like cost.
Yeah, well, that's right.
But there has to be a mapping ultimately
Yeah,
between humans responding in some like gas molecules to costs.
yeah,
Somehow it causally leads to flatlining for nuclear.
yeah.
So it has to be something about humans responding to cost.
Cost is the number one thing,
So it is.
right?
So
And it's a question of, do you want to pay this amount or that amount in your electricity bill?
So the
And if you have a choice, you'll take the cheaper one, all else equal.
So in other words, it is homo economicus. In other words, the strongest
Yeah.
power on humans is cost.
Well, I don't know if I want to say the strongest power.
But I mean, it just seems like it's,
It's a power.
lips,
Yeah.
you
No.
know, and so is it basically?
Yeah. No.
I would.
Yeah.
Right, I mean, not just not just technology.
But we just heard that it was the expensiveness of fixing a hole in a nuclear power. I mean,
I know a little bit about the Vermont one, and I mean, whatever, in the Northeast Kingdom, people don't want reactors irrespective of how they would.
no, but
Yeah. But other people I know, actually, I know a climate scientist who's has a place in Cape Cod and opposed the windmills because he thinks we should do it with nuclear reactors. So, and we're in a funny situation now where nuclear power is not cost efficient, yet it has a huge contingent behind it for almost religious reasons. Somehow they are opposed to those flaky hippies that are against it. Doesn't matter if it costs more now.
And they would say that it's what makes it less expensive. It's all lawyers they need to.
Yeah, but that's obviously not true because you can just see it never was cheap. And which is,
The opposition means that the lawyers and insurance and all that is not clear.
question over here?
Yeah, so I wanted to ask, there was a project you showed where, I think it was when we were trying to predict like what this L would
Yeah, Yeah,
You showed that just producing power with photovoltaics would
Which is also,
at
but there's clearly
a
something.
higher level than the 2022 entire energy production, right?
yeah.
So,
I agree, there's some.
or I guess not production in 2022, but use. So is that purely coming from, like, increases in efficiency? Because we know,
No.
PVs are not 100%, or is it just increased deployment in PV?
It's, well, I'm agnostic about that. The efficiency is generally not the issue. It's cost of making a cell. They all have, the order of 20%. Some technologies get up to 30.
Yeah.
But you're not going to get much better than that anyway.
Sure.
So yeah, what we did there is agnostic to that. We would love to put these things together, to put together cost and deployment and forecast them both in tandem rather than separately. It turns out that's very hard to do because there's a collinearity in the model that you build. And so you can't tell the difference between what's in the demand function and what's in the technology improvement function. It's completely impossible to tell the difference.
This was just based on the cost of like a kilowatt hour of energy production or something.
No, what I showed at the end was based on diffusion. How many have been deployed?
Okay.
And by the way, it was a great what you were saying about nuclear. That's like, you talk to people who work on nuclear, they say just the opposite.
Yeah.
That it becomes